billions of parameters, betting on next word. If it guesses right, you think it's smart. If it's wrong, it's making stuff up. So when we call AI intelligent, what does that mean in engineering terms? In engineering, a system is called intelligent, only because it can do one thing. Without being told exactly how, it can find patterns in data on its own and handle situations it's never seen before. Like teaching a kid what a cat is. Don't need a manual. You just point at cats and say cat. Point at dogs and say not cat. Seeing enough examples, they'll recognize cats on the street. Sounds simple, right? But it took humanity over half a century to make machines do this. The first idea was obvious. Humans write down everything we know, turn knowledge into rules, stuff them into machines. It started with Turing machine in 1936. Give it a manual full of rules and it can do any calculation. Because computing is moving symbols around. Read a symbol, change it. Move one step, repeat forever. But here's the catch. Humans have to write those rules to tell machine, if you see 0, write 1. If you see 1, move right. The machine doesn't learn, it just follows orders. Early AI worked exactly like this, called expert systems. Humans turned knowledge into thousands of if-then rules. Like, if fever over 38, and coughing and high white blood cells, then bacterial infection. But this approach crashed hard. The real world is too complicated. How do you teach a machine to recognize a cat with if-then rules? Cats have a million poses, a million ways to hide. 100,000 rules still won't cover them all. Plus, a lot of knowledge can only be understood through intuition. It's tacit knowledge. You can't write it down as if-then. So when problems got too complex for us to write rules, this path hit a dead end. If we can't write the rules, then let machines find the rules in data by itself. How? Scientists looked at the brain for inspiration. The brain doesn't run on if-then rules. It runs on billions of neurons connected together. They get signals, adjust their connections, and learn patterns. Frank Rosenblatt built the first artificial neural network based on this. It's simple. Each input gets a weight. Add them up. If total passes a threshold, output yes. If not, output no. It's good, but too simple. With only one layer, it could only handle basic stuff. Anything more complex and it failed. Then neural networks kept evolving. 3 big breakthroughs happened. First, networks got deeper. From one layer to dozens, even hundreds. Each layer picks out different features. Feed it a cat picture, let it pass through multiple layers. First layer learns edges and lines. Second layer combines lines into shapes. Third layer shapes into ears and eyes of a cat. Last layer puts it together and outputs. This is a cat. More layers mean more complex patterns. That's what deep in deep learning means. Not about deep thoughts, just about lots of layers. But what if it gets it wrong? Then that's where backpropagation comes in. It starts with the wrong answer, works backwards through all the layers, tells each of the connections, you gave the cat's ear too low a weight, turn it up. Without backpropagation, deep networks are a mess. With that, billions of connections get optimized. Then came data and computing power. 2012, the internet gave us massive amounts of data. GPS gave us brute force computing. Deep learning crushed all the old methods. But AI at this stage was still narrow. The cat recognizer couldn't play chess. The chess player couldn't translate, switch tasks, and you have to start over. But what happened next exceeded scientists' expectations. 2017, Google introduced transformer architecture. It's good at handling sequences, especially language. OpenAI took this architecture and ran a crazy experiment. Build a massive model. Feed it the entire internet. Give it one job, predict the next word. That's it. Guess right, keep going. Guess wrong, adjust the weights. Thousands of GPUs, running for months. Scientists noticed something. As the model got bigger, performance improved along a predictable curve. They called it the scaling law. When it crossed a certain size, something clicked. Some abilities it was never trained just appeared. Suddenly, it could write poems, translate languages, write code. Even though nobody specifically taught it any of this. This is called emergence. It was never programmed to understand language, but to predict the next word with accuracy. It had to compress and internalize all of human grammar, logic, and knowledge. That's today's large language models. Massive next word predictors, trained on oceans of data. This is phase 3 of AI, where we are right now. From one model for one task to one model for everything. If we straighten this line, you'll find that the history of AI is the history of humans letting go. Phase 1, humans wrote every rule. Phase 2, humans only provided structure. Machines learned rules. Phase 3, humans don't specify the task anymore, just let abilities emerge on their own. Our role changed, from writing rules to providing data and power. That's how intelligence evolved. But there's a cost. Emergence needs scale. Scale needs computing power. Computing power needs chips. Now, the whole world is fighting over the H100. Next video is about why it's worth tens of thousands and the secret chip war between nations. See you soon.